So, good morning, student. Uh, Today we'll start our class. So like for today's topic of discussion will be mostly on calculate the partition functions, and from partition functions we are going to calculate several types of thermodynamic property. Okay. So one second. Okay. So so today's our topic of discussion will be briefly on how to calculate partition function of different systems and from and from there to calculate thermodynamic properties. Okay. So most of the problem that basically the problems are basically taken from the last year assignments. So these problems were mostly based on this area, like how to calculate the partition function and like for different types of system, and from there we have to like calculate the equilibrium properties of that particular system. So uh, one second, let me just check. Yeah, reforms. So let's start our problem number one for today's class. Okay. So uh, so problem number one. Okay. The molecular partition function of a system is given by T equal to KBT by HC 3.2 into L pi square and KBT by L square 3/2. Okay. Now where the symbols have their usual meaning. The heat capacity at constant value for this system is, for one more obviously, so 1 6 are option 2, 3 are option 3, 3 are by 2, option 4, 9 are by 2. So these are the four options given. Okay, so okay, so basically, yeah, you have to calculate basically the heat capacity. Okay, So okay, so in order to calculate the heat capacity, first thing that we have to calculate is the internal energy, right? From the internal energy, we know we can calculate the heat capacity, because heat capacity is nothing but at constant value CV equal to du dt, right? So so from there itself we have to calculate the heat capacity, right? So uh, okay, so for that first so okay, so first we have to write the internal energy, okay, like expression of the internal energy in terms of heat capacity, okay. So how to do that, okay? So mm, so first we have to derive the internal energy, okay. So how to derive the internal energy? So first let's do the derivation. So we all know, let's suppose there are many different energy states are there. Let's suppose epsilon 1, epsilon 2, epsilon 3, like this, dot, dot, dot. So if there are several energy system like this, then the average energy, that is E bar, will be summation of all the energy into e to the power minus beta EL plus Q, right? So here is the energy levels of the molecule. Okay, like in this problem, it's applicable for molecule. That's why I've written the molecule. and q is the basically is the partition function, right? E to the power beta er, that is the partition function. Partition function. Okay. Now what we do? We can write. Now let's do. Now we have to write this average energy in terms of a, only in terms of a partition function, not like this summation like this. Okay. So to do that, what we have to do? So let's first find out. Let's find what is del q del beta. Beta is already know, that is 1 by a dt, right? So del q del beta will be del beta of summation over e to the power minus beta epsilon of r beta. Now this is summation over I. Now this we can write is summation over I to the power epsilon of r e to the power beta e power n. Now this we can write it like 7 r e r e to the power beta e r. So now, so we already know that E bar uh, is nothing but, I mean, from this relation we can write, we can know that EI equal to power beta EI is nothing but Q angular bracket E. So if we substitute this thing here, then we can write del Q del beta equal to minus Q E bar, right? So now from here, from this relation, we can write E angular E average equal to 1 by Q del beta, right? And now if n numbers of molecules are there, then then we can write it. Then we can write it like this. For n numbers of molecules. And numbers of molecules. Okay, so like if there are n numbers of molecules, so like each of the molecules would be having this average energy E, right? I mean angular E would be the average energy for each of the molecules. Okay, so the total energy would be nothing but is the internal energy of the system. Okay, so U would be basically that is the internal energy. Nothing but A E. That we can write it like minus n by q del q del beta, right? So this is one way. Now we can further simplify this expression. Now let's again we can rewrite del q del beta as del beta of ln sorry e to the power ln q, right? Because e to the power ln q is equal to q, so we can write q as e to the power ln q, right? Now if we do the derivative, it simply gives us e to the power ln q into del ln q by del beta. And e to the power ln q is, you already know, that is q, right? So it is given del ln q by del beta. So now we can write the internal energy U as, now if we substitute this thing here, which basically gives us U equal to minus n 1 by q delta ln q by del beta. Okay. which is nothing but minus n delta ln cube by del beta. Okay, now now this we have been down in terms of derivative of beta, right? But in our problem we can see the expression here. If you see, uh, here as you can see, this expression is dependent on the temperature. Okay, so what we can do, we can write this thing in terms of temperatures also, right? So what we can do, we have to, so we can write u as, so we can just like substitute beta in terms of temperature kBT, right? So how we can do that? We have to simply do this kind of this. So we have to substitute beta equal to 1 by kBT in this expression, which basically gives us the final answer. So del beta, we can write it as del T of del beta by del T, right? And that simply gives us del T by del beta is nothing but 1 by del, this is nothing but 1 by del beta by del T, right? So which gives us minus kBT square, right, by del T. So now if we substitute this here, which gives us basically internal energy U equal to minus n equal to minus kBT square delta ln Q del T equal to n kBT square delta ln Q by del T. This basically gives us the internal energy of the system. Okay. So now we got the internal energy. Okay, so now let's go back to the problem. Okay. So now in the problem, the partition function is given by this, right? So this is basically the expression of the partition function. Okay, so now what we have to do, let's first write the partition function. U t equal to ABT by 8C 3 by 2 8 pi square m KBT 8 square 3 by 2. This basically gives us if you have to simplify it, basically gives us ABT by 8C into 8 pi square and ABT square by 8 square 3 by 2, which gives us QT equal to 8 pi square and AB square 8 cube C 3 by 2 TQ. Okay. This is the expression of the partition function. That is QT is, let's consider this whole thing as a constant A. So QT would be simply A into TQ, right? Now so now we have already found QT. Now we have to first, like we have already discussed that specific heat is nothing but just the temperature derivative of the internal energy. So first we have already derived the internal energy, the form of the internal energy in terms of partition function. Now we have actually used that formula. So what is the formula? U is n kb t square delta ln q by delta t, right? So now if you do the derivative, this is the q. So if you do the derivative, it will be n kb T square into so ln qt. So first let's derive ln qt. So ln qt. So ln qt is nothing but a into tq, right? That we have done here. Okay, that same thing. So this gives us ln a plus 3 ln t, because ln t cube, and if you do, if inside the ln there is a power, if there is power exists, then it will come as a multiplicating factor, right? Property of log. So now I have to do the derivative, so just substitute it here. Del 2 ln a plus 3 ln t. This basically gives us n kb t square, and this gives us 3 into, so del t of ln t, this gives us n kb t square into 3 del t of ln t gives you 1 by t, so u basically gives you 3n. So here was there, so I forgot that one. So n kb t square, so n kb t. So this is basically the form of the internal energy, n 3n kbt. Okay. And now from here we have to calculate the Cv. Okay. So Cv, as we have already discussed, it's nothing but the temperature derivative. So what will be the Cv? Cv is del U del T, right, at constant volume. This is the definition of Cv, right? So now Cv would be simply del T of Cn kT. Cv is 3n kb, right? And now in the problem it's mentioned that there is 1 mole of molecules, right? 1 mole of molecules. So for that, n should be number, Avogadro number, molecules are there, right? So Cb equal to that 3 Na Kb. So 3 Na Kb basically gives you R. So we already know R equal to Na by Kb, right? So that thing we have used here. So Cb is basically 3R. Okay. So the correct answer will be this 3R, right? So this is the correct answer. So let me just tell the whole thing from the beginning. So in the problem, the molecular partition function of a system is given. This was the expression, and this was the expression. And from there, you have to calculate the heat capacity at constant volume, right? That means Cv. So this is the formula of Cv. So this is like Cv is a constant heat. So this is the formula of Cv. So Cv is basically del U del T of T is the temperature at constant heat. So in order to calculate the Cv, we first have to calculate the internal energy, right? How can we calculate the internal energy? So for that, we have to go back to the basic definition of partition function, and we have to write that thing out to calculate the average energy of a system. Okay. So first we have let's suppose these are the molecular energy levels, and from there we have first calculate the average energy of the system if there is one molecule, and from there we have done some algebraic manipulation, and from there the average energy we have got in terms of only partition function, that is minus 1 by q del beta, or beta is 1 by kBT, right? And if there is n numbers of molecules are there, then each molecule definitely has the average energy. So the total energy would be nothing but actually the internal energy of the system, that is n into the average energy. and that basically gives you this expression. Now we can further now we have further simplified this expression. So write del q del beta in terms of log of ln of q, and from there we got the final expression of internal energy, which is nothing but this, u equal to n kbt square del ln q by del t. Okay. So now we got the internal energy. Now from there, we also know the partition function for the system. So what we did first, we have first we have first write this partition function in a easy to understand way. So we have made this whole thing as a constant a, because all of these expressions contains constants only. So we have write all these things as a constant a, and this becomes our total expression. Now what we did, now we first calculate the internal energy. So this is the basically the expression of internal energy. So this gives you this, and from there you write the internal energy equal to 3 kBT. Okay, we got the internal energy. Now from internal energy, simply if you do the time derivative with respect to the volume, gives you the specific heat at constant volume, which is nothing but 3 NP. And in our problem, it is already mentioned that if you see here, it's already mentioned here that we have to calculate it for 1 mole, right? So 1 mole means the number of molecules should be the Avogadro number, right? N equal to Na. So we have put it like that, N equal to Na, and Na into Kb is nothing but the R, ideal gas constant R. So from there Cv equal to 3 R. So this is how you should solve the problem. This problem. So we have done the problem number 1. Now we have moved to the problem number 2. Okay. So problem number 2. Now let's write the problem number 2. See that level quantum system with energies U1 equal to 0 and E2 equal to E. Now for this system, what you have to do, the thermodynamics energy of the system is given by, you have to choose the option, there are 4 options given, minus kb t ln 1 plus e to the power minus beta e. Option B is AB T ln 1 plus e to the beta minus beta B. Option C is 1.5 ABT. Option D is E minus ABT. These are the four options given. So let's read the problem. So there are two level quantum. So there are two states are here basically. So one has n equal to 0. Sorry, one has e1 equal to 0. One is e1 equal to e. So e2 equal to e. So for this system, you have to calculate the Helmholtz free energy. So how to do that? So first, for this system also, what we have to do, first we have to calculate the partition function, and from there itself we have to calculate the Helmholtz free energy. But we don't know the Helmholtz energy, right? Helmholtz energy expression in terms of partition function, right? So let's first derive the expression of Helmholtz free energy in terms of partition function. Okay. So how to do that? So let's first write. Okay. So the Helmholtz free energy A, right, is defined as A equal to U minus Ts, where U is the internal energy, T is the temperature, S is the entropy. Okay. So these are the expressions that are given. So now from this problem, we have to calculate. So the Helmholtz free energy, like this is in terms of internal energy and entropy. So now from here you have to find the expression of the Helmholtz free energy, which will be in terms of partition function. Okay. So what we can do from here? So one thing we can do, we have already knew, right, the expression of internal energy in terms of a partition function that we have did in the previous problem. Okay. So according to the previous problem, the internal energy expression U is defined as minus m delta ln Q by del beta. This is a fixed coordinate. So beta equal to 1 by kBT. Now the entropy S equal to, so we can write entropy. So now we know the internal energy U, but here is from this expression, as you can see, we not only need the U but also we need the expression of S, right? So how we can do that? So we already know like the fundamental definition of entropy, right? So the fundamental definition of entropy S is given by S equal to Kp ln sigma. So this sigma, big sigma, is but nothing but the number of micro states. I hope you already knew about the microstates. So basically, microstates are nothing but like like a system contains molecules, atoms are particles, right? So in a same system, the particles can be arranged in different types of way, right? So each different types of arrangement, we can consider it as a different microstate of a same system. Okay. So that we have already discussed, like in previous tutorial sections also. Like, so this sigma is nothing but the but how many number of microstates are there for a particular system. Okay. So that number is basically denotes by this sigma, big sigma. Okay. Now, now for a canonical partition function Q is this. Q is e to the power beta ei. Canonical partition function. Then uh, so let's denote it by big Q. Okay. So mm, so now you can write. So now for this case, we can write if this q already we knew for a canonical partition, the canonical partition function. We can write this entropy as like this. So AB ln q plus ut. Okay. I mean the derivation of this entropy from this step to this step is like beyond the scope of the discussion for today's class. Okay. So just remember this fact. Okay. For a canonical partition function, microcanonical system, for a canonical system, the entropy is, if you know the partition function Q, the entropy basically can be expressed like this equation. Okay. Now, now what you can do? Now we can simply write, right? You can simply now do the uh, simply can do substitute both this entropy and internal energy into the expression of Helmholtz free energy, right? So A will U minus Ts. So we can write T as N AB ln Q plus U by T. So A will be U minus N AB T ln Q plus U. Sorry, so it will be minus U. So this basically gives us U basically cancels, which gives us minus N AB T ln Q. Now this is nothing but the orange free. Okay, so this is given by the Helmholtz free energy. So we have derived the Helmholtz free energy uh, in terms of the partition function Q. So now what we will do? Now we will go to the next step. Okay. So the next step is we have a particle which can either be in state in E1 or it can be state in E0, E2. E2 is basically E. So let me first write it. So for our problem, there are two energy states are there. One is E1 equal to 0 and second is E2 equal to E. So in that case, we have to first calculate the partition function. So which is nothing but Q basically is e to the power eta E1 plus to the power beta Right, because Q is nothing but the summation of all the energies, right? Right, Boltzmann fact. Like this is basically each according to it for this system, two-level system, and there is only single particle is there. Like for a single particle, I think in this problem they have asked to calculate. Yeah. So no particle number is given, so have to calculate this atmosphere for a single particle. That means so the partition function is given by this, and I mean the expression of partition function will be this. Now from here, T would be simply e to the power minus beta 0 plus e power minus beta e, which should be 1 plus e to the power minus beta e. Okay, this is the partition function. Now, so we have calculated the partition function. Now from we have to use this thing here. To get the Helmholtz energy. Okay, so Helmholtz energy A is basically then have to be minus ABT ln Q. So minus ABT ln would be Q would be 1 plus e to the power minus beta E. This simply means that A would be simply minus ABT into ln. So I guess let's see the problem. So okay, so we don't have to further simplify it. So this would be the answer. Okay. So the answer would be this one. It's option A, right? So the answer would be option A. Okay. Yeah. So answer would be option A. Yeah, this is fine. So how we solve this problem? So in the problem basically they have tell us to find out the Helmholtz free energy for a two-level system, single particle. Two states are E0 and E. Now, so first we have basically write. So for this system we can calculate the partition also, right? But we don't know what is the expression of the Helmholtz free energy in terms of partition function, right? So what we did is first write that thermodynamically the expression of Helmholtz free energy, the definition, thermodynamic definition, and from there we know the internal energy or S in terms of partition function Q. So we have basically substitute it, and after doing all of that, we got the got the Helmholtz free energy in terms of partition function Q is nothing but minus n kBT ln Q. Now from there, first we have find out a Q. That is the summation of summation of the energy to the power minus beta E. This partition function that we calculated first, and after substituting it, we got the Helmholtz free energy, which is this. So the correct option is option A. Okay. So this is it. Now we move to the problem 2 is there. Now we move to the problem number 3. Problem number 3. Problem number 3. So problem number 3 gives us one second. Let me write the problem 3 first. Consider a system of n number of non-interacting distinguishable where each particle can be in three energy layers. Okay. The lowest one is called the ground state, is non-degenerate, and its energy is considered to be zero. Now the middle one, that is the ground state, on the middle state, the middle one at energy E is doubly degenerate. Okay, first though the ground state was not degenerate, but the middle state here is doubly degenerate. Okay, doubly degenerate. The highest one at energy 2E is triply degenerate. Now considering canonical ensemble, calculate the internal energy U. Okay, so and the option, let me also write the options. Option was E to the power minus beta E into 1 plus 3 E to the power beta E by 1 plus 2 e to the power minus beta E plus 3 e to the power minus 2 beta E. That is option A. Option B is 2e to the power minus beta E 1 plus 3 to the power minus beta E by 1 plus 2 to the power minus beta E plus 3 to the power 2 beta E. Option C is 2ne to the power minus beta E by 1 plus 2 to the power minus beta E plus 3 into e to the power 2 beta E. Option C. Option D is 2n e by 1 plus 3 e to the power minus 2 beta E by 1 plus 2 e to the power minus beta E plus e to the power minus 2 beta E. So these are the four options are given. Okay. So basically, so here in the problem, there are n numbers of non-interacting particles is there, right? It's not like one single particle. N numbers of particles are there, and for this n numbers of particle can have three levels. There are three levels of energies there, and each of the energy has different degeneracy level. So for better understanding, let's just let me just do the thing. So first is E1, E1 is 0, E2 is E, and E3 is 2E. And each energy has, and like for E1 equal to 0 has degeneracy G1 equal to 1, E2 has degeneracy G2 equal to 2, and E3 has degeneracy G3 equal to 3. So these are the energy levels and their respective degeneracy are given. Now from here you have to calculate the partition function. So partition function Q is summation over I Gi to the power eta EI. This is the expression of the partition function. So now from here, so now, okay, so here beta is already know, beta is 1 by k dt. Okay. Now, so partition function first you have to write Q is so first case, so Gi is the degeneracy already discussed. So Gi equal to G1 into e to the power beta E1 plus Q2 into to the power beta E2 plus E3 into to the power beta E3. Now this will be simply 1 into to the power beta into 0 plus 2 into to the power beta E, here its energy is E, plus 3 into e to the power 2 beta gives us Q equal to 1 plus 2 to the power beta E plus 3 into to the power 2 beta. This is the expression of the partition function of the system. So now we can calculate the internal energy once we got the partition function. So it will be simply minus n delta ln q del beta. So this is the internal energy U. Okay. So now what you can do, we can write, so first U as minus, so ln t you can write it ln as 1 plus 2 to the power beta E plus 3 to the power minus 2 beta E. Now, okay, so now I have to do everything very carefully, okay, because ln q, right? Ln q, now I have to do the derivative. So let's first do the derivative. So delta ln q by delta beta. Let's do it step by step. Okay, so del beta of ln 1 plus 2 to the power beta u plus 3 to the power beta u. This simply to the derivative gives you 1 plus power beta e plus 3 to the power minus beta e. And here it gives you 0 minus 2e to the power beta e minus 6e to the power minus 2 beta e. Del ln q by del beta. Now del ln q del beta would be minus 2e e to the power beta e plus minus 6e e to the power 2 beta e by 1 plus 2 to the power minus beta e plus 3 to the power minus 2 beta e. Okay, so this gives you the derivative ln cube with respect to delta cube. So now, okay, now we have to calculate. This is the formula for n number of particles, right? Internal energy for n numbers of particles. Okay. So now this is it. Now we have to find out the EO. So you would be when delta LLP by delta beta, right? So n would be minus 2e to the power beta e minus 6e to the power minus 2 beta e by 1 plus 2 to the power beta e plus 3 to the power minus 2 beta e. This is it. So now this is B, this is B would be simply 2ne e to the power beta e plus 1 plus 3 e to the power beta e into 1 plus 2 to the power beta e plus 3 to the power 2 beta e. So this is basically the internal energy. So let's check the expression. So I guess the correct answer would be this one. 1 plus 3, right? So 1 plus 1 plus 1 plus 1 to the power. So option A. So option A was the correct answer for the system. Okay. Okay, so let me just explain it well once again how we have done it. So these are the three energy states that are given in this problem. 2e, E and 0, and each have degeneracy level, like state 1 has 1, state 2 has 2, state 3 has 3 degeneracy level. So now from there we have to calculate the internal energy for the system. So how can you do that? So first and foremost thing to do is calculating the partition function, and this is the partition function. Like previously we have used the partition function by considering the fact that there is no degeneracy exists in the energy levels, but for this problem since the degeneracies exist, so we have to consider that fact into the expression of the partition function. So this is the modified formula where Gi is the number of degeneracy in the ith energy state. So Q would be simply the summation of Gi into e to the power minus beta E here. Okay. Here is the energy of the ith energy state, and if you do the summation, Q would be, so this is basically G, this is not Q, G1, G1, G2. So for this G level system, the total and the partition function would be this. Partition function would be this. Now, as we have calculated the partition function, you already know the internal energy expression that depends on the partition function Q, and n is the total number of particles. So we have used that expression. U is basically nothing but minus n into delta of ln Q by delta beta. Beta is already known 1 by kBt, and ln Q first we have calculated. Then from there we have calculated del ln Q by del beta, gives this expression, this one. From there we have calculated the multiplying n, we got the So you by doing some simplification, you got the total internal energy level. So this is how you should calculate for this kind of problem. First and foremost, you have to find the partition function, and from there itself you have to calculate the other things that has been mentioned in the problem. So this is the problem we've done. So now we have to go to the fourth problem. One second. Okay. So now we'll start the problem number 4. Okay. So what problem number 4 tells us? So problem 4. So consider the question 3, calculate the entropy of the system. Option A is KB and then 1 plus E into the power beta E plus E to the power minus beta E plus say with expressions 2n into 1 plus 3 to the power minus 2 beta E by 3 into 1 plus 2 to the power beta E plus 3 to the power minus 2 beta E and 1 plus 2 to the power minus 2 beta E 3 into 2 to the power 3 beta E plus 1 plus 3 to the power beta E 3 into 1 plus to the power beta E plus 3 into the power beta E. Option C is KB and then 1 plus 2 to the power beta E plus 3 to the power 2 beta E plus 3 sorry, mistake to the power beta E here. So here e to the power minus beta multiplied here also. e to the power minus beta e 1 plus e to the power minus beta e by t into 1 plus 3 to the power beta e plus e to the power minus 2 beta e ct and cubing ln 1 plus 2 into the power beta e plus c to the power 2 beta e plus 2 and e to the power beta e 1 plus 3 to the power beta e by t into 1 plus 2 to the power beta e plus 3 to the power minus 2 beta e. Okay. These are the four expressions in there. So what you have to do, like the problem was same with three energy system, because here it's mentioned. You can see that the question is so similar three energy system. And now instead of the Helmholtz free now instead of the internal energy, you have to calculate the entropy of the system. Okay, so how we can do that? So so in order to do that, so this is so entropy. So previous, just me just write the results that we got from the previous one. So according to the previous problem, so according to the previous three degenerate three energy, just only energy, three energy state problem. According to that problem, partition function Q is given by 1 plus 2 to the power minus beta e plus 3 to the power minus 2 beta e. Okay, and this is one result. Second result is internal energy, that is 2n e to the power minus beta e into 1 plus 3 to the power minus beta e, that is divided by 1 plus 2 to the power minus beta e plus 3 into e to the power minus 2 beta e. So these are the two results that we have got from the previous problem. Now we have to use this result. I mean, let's see whether you have to use it or not. Okay. Now in this problem, we have to calculate the entropy, right? So now, so for this type of canonical problem, we have already mentioned the formula of entropy in terms of the partition function, right? And that formula is nothing but S equal to, for in if there is n number of particles are there, so that formula is n kb ln q plus u by t, right? This is you already knew, we have already discussed. Although the proof is not relevant, like for I mean it's not relevant like the scope of discussion for this tutorial. So now, but we can use, we can like say use the formula. Okay. So now, in the formula you can see we need both the expression of Q, which is already given here, and also the internal energy is given here. Basically, you can just use these two results, substitute in this expression, and we have to do some algebraic manipulation. After that, we will be getting the expression that one of the expression that is given in the options. So now, so in order to do that, first what you have to do, S equal to, have to write S equal to n kb ln 1 plus, so we are just first you have just substituting this this partition function here, then the internal energy here. Okay. So if you do that, we get that e to the power 2 beta e plus 3 into e to the power 2 beta e plus 1 by t into so internal energy of to write 2 n e to the power beta e into 1 plus 3 to the power beta 3 to the power beta e by 1 plus 2 to the power beta e 3 to the power beta e. So here you already know. So uh, we will use we will use some some kind of algebraic manipulation. Like we have to match this expression of s with one of the options that is given, right? So to do that, we have to do some simplification. So you can write beta is equal to 1 by kbt, right? So that means you can write inversely t as 1 by kb into beta, right? Now if you substitute this thing into this expression, it simply gives that s equal to n kb. The first term will be as it is, 1 plus 2 to the power beta e plus 3 into e to the power 2 beta e. First term will be as it is, and for the second term we can write it like this: kb into beta into 2n into e to the power beta e plus 1 plus 3 to the power minus beta e, and in a denominator it would be simply 1 plus 2 to the power minus beta e plus 3 into to the power minus 2 beta e. So this would be in the denominator. Okay, now so I have used that fact here actually. Now we have again what we can do. Hmm. Now what you can do, you can again write it like this: s equal to n kb over 1 plus 2 to the power beta e plus 3 to the power 2 beta e plus, you can write it like simply as 2 ne to the power beta e by t into 1 plus 3 to the power beta e, and the denominator as 1 plus e to the power beta e plus 3 e to the power minus beta e. Okay, so this means uh, the correct answer would be, that means, okay, so correct answer would be simply 1. So option will be option A, right? Option A would be the correct answer. Okay, fine. So I hope all of you understood how to solve this problem. Like the similar problem, similar case, that is like question number 3. But here we have to calculate the entropy. So the same results we have been using, we've been following the same result that I have used before. We can be used here also. And here the entropy, this is right in terms of Q and internal energy U. Just after substitution and doing some simplification, I got the expression of entropy. So This is the question number 4 is done. So now now we'll be going to the question number 5. Question number 5. The molecular partition function of a system is given by Qt equal to AT to the power 4, where A is a constant, okay, and the internal energy is for 1 mole is the given options. In one of the given options, 3RT, B is 6RT, C is 4RT, and D is 2RT. So these are the 4 options given. So okay, so internal energy. So now, okay, so answer is Qt, partition function is AT to the power 4. Okay, so A is a constant here anyway. So now, okay, so internal energy I've already discussed, right? E equal to minus n delta of ln by del beta, which alternatively we can write in terms of for this problem it would be easier for us if we write it in terms of in the terms of the derivative of t naught in terms of beta. So for that case it should be simply n kb by the minus sign will be 1 in that case, n by del t, because beta we already know 1 by kbt. So okay, so that would be the expression of the internal energy, right? Now what I have to do, okay, so for 1 mole n would be Na, so Na into Kb would be gives you R, the real ideal gas constant. Now so you we can write it Na Kb square T square delta N by delta T. This means it should be R, sorry, Kb square is not just Kb, R T square delta N by delta T. Now here first just evaluate, so the Q is given here, A by T to the power 4. So Q would be, so ln Q would be ln A into T to the power 4, ln A plus ln T to the power 4, that gives you ln A plus 4 ln T, and then ln Q equal to, now I have to do the derivative, which is simply Qt square ln derivative of temperature ln plus 4 of ln T, which gives you Q equal to Q, sorry, this is R, this is R T square 4 into del T of ln T So ln t gives you 1 by t, right? So it would be, so r t square into 4 by t gives you 4 r t, right? So the correct answer would be 4 r t, that means. So this is the correct answer, 4 r t. So how I've done it? So like partition function is already given for this problem. Is a some constant into t to the power 4, and internal energy expression we have already know in terms of t also, in terms of beta also. But whatever according to the problem is needed, we can use that. Okay. Now for 1 mole, just that n equal to Na will come, and Na into Kb you already know is R is the ideal gas monster. So Na into Kb becomes, gives you R into T square by delta ln Q by del T. And del ln Q first is nothing but 80 to the power 4. So you see this. So this is the ln Q. Now we have just substitute ln Q here. It gives you, so that means U is nothing but R T square 4 into R T square 4 into ln T. Now ln T gives you 1 by T, so R T square 4 into 4 by T gives you 4 R T, right? This is how we solve the problem. So the um, problem number 5 is done. Now we go to the problem number 6. Consider a free Brodel quantum system with energies E1 equal to 0, E2 equal to E, E3 equal to 2E. Now the Helmholtz free energy of the system, the knowledge energy of the system is given by beta equal to 1 by capital from the problem expansion is one of the options here. So options are by AB ln 1 plus to the power minus beta E plus to the power beta E is minus KB ln 1 plus beta e plus beta e. C is 1.5 kDT and D is equal to minus kV. So these are the options given. So you have to basically calculate the Helmholtz free energy system. Similar way, so okay, just like question C, similar here also 3 energy systems are given. Here there is it's not degenerate system like that question 2 we have deal with the degenerate system, but here fortunately it's not degenerate. So the problem becomes simpler for us also. So these are three state. So one is E1 having 0, E2 having E, and E3 having 2E. So now first step to calculate the Q partition function, that is equal to the power. Now here as this it's not a degenerate system, so we just use this formula, which gives us e to the power beta into 0, because C1 is 0, e to the power beta E2 is E, and e to the power beta E3 is 2E. So this basically gives us 1 plus e to the power beta E plus 1 plus e to the power 2 beta E. This gives us the Q, and so from here we can calculate the Helmholtz free energy. So we have already discussed, right, in this problem, the expression of Helmholtz free energy. So question number 2 here. So here this is the Helmholtz free energy of derived, right? This was the expression of Helmholtz free energy, A minus infinity ln. So we have to, for this problem also have to use the same formula. So here also A equal to minus kBT, because this is a single particle problem, so N will be 1 here. So A would be minus kBT ln 1 plus e to the power beta E plus e to the power 2 beta E, and this is the Q substituting here gives us this. Now from here A would be simply minus kBT ln I think we don't have to further simplify it, so one of them would be the correct answer, so that would be, I think, this one. This is the same options. Okay. KBT. Okay, so one of these options, there is KBT. I missed the KBT actually. So this is the KBT. So option B would be the correct option. So this is like the similar type of problem that we did earlier, so 3-level system, right? So here it's simpler because there is no degeneracy exist for this system. First you have calculate the Q, then from there you have calculate the Helmholtz free energy, right? So this is it. So question number 6 is completed. Okay. So now since we got still half an hour remaining, so what we can do, we can discuss from some problems like this current assignment problem, assignment number 6, from the problems assignment number 6. We can discuss some of the problems. Okay. So let's start. So okay, so let's start from problem 1. That is, this problem set is also mostly deals with partition function and all. So, let's start the problem. So the translation partition function of a term is 8 into 10 to the power 33 and 3700 Kelvin in a volume of 0.064 meter cube. Now, what is the thermal wavelength value in meter? So, what is the thermal wavelength value in meter? Okay, so I'm going to write a question in here anyway. So the options are: option A is 10 to the power minus 12, option B is 4 into 10 to the power minus 12, option C is 2 into 10 to the power minus 11, and option D is 2 into 10 to the power minus 12. So these are the four options are given. So now I have to basically calculate it from here. Okay. So now this kind of problem, like we have already like discussed in the like the last tutorial class. Okay, so how to do that basically? So we already know that uh, translational partition function, that is basically this one, z translational. So let's just, before that, just write what we have to find out. So we have to find out the thermal wavelength, right? So what is the given? So Z translational is given, that is 8 into 10 to the power 33 for each atom, and temperature is given 3700 Kelvin, that is a very high temperature, and volume is 0.064 meter. Now, translational partition function we have already discussed in the previous tutorial. The Z translational, that is the translational partition, is simply by is V by lambda thermal whole cube. This is applicable for a single particle in volume V. Okay, this is the translational partition function here. So lambda thermal, so we like for our problem to calculate the lambda thermal, and this thing is only this expression is only applicable at high T. So lambda thermal will be V by Z translational 1 by 3. Okay, so now from here, lambda thermal will be 0.064 8 into 10 to the power 33 1 by 3 8 into 10 to the power minus 36 1 by 3 into 10 to the power minus 12 meters. Okay. So this is how you have to solve the problems. Basically, the volume and partition function are already given. So you have to use this to formula this one formula by Z translational will be V by lambda thermal whole cube. It's nothing but a partition function single particle which is confined in a volume V, and only this formula is applicable at high temperature. From there lambda thermal you can calculate which is 20 to the correct option would be option G. Now goes to the question 2. Question 2. So what is question 2? Question 1 is given. So now it's so question 2. Gives paradox in statistical mechanics is related to option A, additive property of the temperature. Option B, additive property of the energy. Option C would be additive property of the momentum. And option D would be additive property of the entropy. So these of the 4 options are given. So now what you have to do basically simply which should be correct. So how to do that? So here gives paradox. Okay. Now before doing this, let's just simply recall what basically Gibbs paradox is. Okay. So what is Gibbs paradox? So according to this paradox is that if suppose two gas let's suppose a chamber is there, a gas chamber. Okay. And there's a partition between it. Two similar types of gases are mixed here, V1, and here it's V2. Now, what theoretically what we have find out before the solution of the Gibbs paradox, what's simply coming out that when this is now demixed, like these two partitions are not mixed with each other. Now if you simply remove these two partition, which results into the mixing of between these two gases. So what happens there that theoretically because of the mixing there is a entropy increase was there, right? Delta is mixing, that is the entropy of mixing. Now in this case, although these two gases are in same same species, so even if you open this barrier, physically they're not should in terms of in reality there should not be any change in entropy, but when you are calculating this change in entropy using our theory, then you can see there is a change in entropy even though these two gases are exactly same each other, each gas, still there is an increase in entropy. So what is the problem here? So this paradox basically resolved by the resolved by the by considering that the case this identical particle, the distinguishability of this identical particles. Okay. So uh, previously when you are using this formula of entropy, we are not considering that fact that the particles can be distinguishable, right? So this distinguishability condition was not there previously. But because of that, when you theoretically calculating the change in entropy due to the mixing of these two similar types of gas, there is an increase in entropy. But after considering this distinguishability criteria, we find out that this paradox resolves quite well by making the L delta S mix equal to 0. Okay. So um, so now here, so the main thing is for this case, we have to deal with some. So basically here, this thing we are dealing with basically the extensive quantity, right? That means extensive means uh, additive quantity, whether you can say. So the because of that, whether when you mix this thing, the entropy change was not zero, right? As it's additive term, additive property, right? And out of the given options, the only extensive property here is the entropy, right? From the four options that is given. So that's why the correct answer would be the entropy. So let me just write it here. So Gibbs paradox occurs as we incorrectly treat identical particle as distinguishable particles, right? That's the reason we are using the wrong expression of S, because as these are identical particles, simply these are not distinguishable, right? So which actually results into correction into that entropy expression, and if we do that, we'll find out that for this identical gas, when mix, the delta S mixing will simply become to 0. Now, so for this problem, uh, so the here this basically leads to around 150, which is not extensive, right? That means not additive. Sorry, which is actually extensive. Additive, which is extensive, sorry, not extensive, it is extensive. So that means the only additive property here in the options also, the additive property of the entropy, the correct option. So option D. Now option C. Question C. Okay. Option to question 3 is the molecular partition function for a system in which the energy levels are spaced by E is option A 1 by 1 minus 2 minus beta E. Option B is 1 by 1 plus to the power plus sorry. So first option was plus, second option was minus, third option is 1 by 1 minus, D is 1 by 1 plus. So these are the 4 options. Okay. So now what you have to do, the partition functions. Okay. So how can we do that? So can use a geometric series also. Okay. So what you have to do here? Now here the energies are basically equispaced. Okay. So equispaced. So let's suppose these are the energy levels. If this is 0, this is E, this is 2E, this is 3E, so like this. Okay, so because each of the energy space should be E. The energy space to equispace. So the energy space should be looks like this, right? Now for this system, there is like infinite like this system energy supply N. So now for this kind of systems, the partition function Z is, we already know, is e to the power beta EI. Now for here should be n equal to 0 to infinite e to the power minus beta Ne. So n0 makes it e to the power b to the b into beta into 0. That's it becomes e to the power minus beta into 1 e and 2 e and 3. So like this it goes on. So this would be the expression. Now here, okay. So now here you can further write it like this. So so it can be written like this: 1 say to the power minus 0 plus e to the power minus beta E plus e to the power minus beta E. 2 beta you can write it like this whole square, similarly to the power minus beta E whole cube plus like this you can write. So it simply gives us 1 plus e to the power beta E plus e to the power beta E whole square plus e to the power minus beta E whole cube plus this. So this you can write it, you can take it as a this is equivalent to a geometrical series, right? Geometrical infinite geometric series, right? So where for a geometric series you already know 1 plus r r square plus r cube, basically summation of n equals 0 to infinite up to the power n. You can write is 1 by 1 minus r, right? For the given time, mod r should be less than 1. Here for this case also, the 1 by e to the power beta E is, if you take the mod value, should be less than 1, right? Because e to the power beta is in the denominator, which makes it less than 1. Because this is greater than 1, which makes it this thing less than 1 by this thing. So So now this geometrical rotation series we will be using here. So this basically gives us z equal to 1 by 1 minus e to the power beta e. Because for our case, the e to the power minus beta is simply the factor of the multiplication, which gives us this. So the final answer will be z equal to this. Okay. So I have all of you understand how to calculate the partition function of the system. So now we go to the last problem, which is the problem number 4. So problem number 4. So problem number 4, let me first write it. The value of molecular partition function of for rotation at 300 Kelvin, sorry, 3600 Kelvin is 19.06. What is the value of what is the value of the characteristic rotational temperature theta r. Option is 188.88. Option is 94.44 Kelvin. Option C is 196.92 Kelvin. Option D is 96.96 Kelvin. Okay. So these are the 4 options given. Okay. So now how to do that? So okay. So for that here, is the diatomic molecule, right? So for the diatomic molecule, the energy states for the J energy, like each energy state has some degeneracy, right? So so the rotational energy levels is given by, so for a diatomic molecule, the rotational energy levels are given by using equal to j into j plus 1 h whole square by 8 pi square 5. So here j is nothing but 0, 1, 2, here QR. So if these are the energy state, J is basically the rotational quantum numbers here, okay, 0, 1, 2, 3. So for this case, the rotational partition function QR would be simply j equal to 0 to infinite 2j plus 1 to the power ej by kbt. Okay. So now here 2j plus 1 is the degeneracy. So each jth level can have 2j plus 1 is 2j plus 1 number of degeneracy. Okay. This is the degeneracy. Now, one thing is important here that this formula is only applicable at lower temperature, but at higher temperature, so this expression would be simplified. Okay. So for high temperature, where PVT would be greater than 8 pi square I. For that case, QR would be simply T by theta, where theta is basically known as characteristics rotational temperature, characteristic rotational temperature, and the expression of theta is basically h cut square by 8 pi square I kb. This is the expression. This is the QR expression. Okay. These two are given. So now theta will be. So now in our problem we have to find out this characteristics rotational temperature right here. So now, and in the problem what are given? Rotational partition function or rotational. So the temperature is also high, very high, 3600 Kelvin. So our approximation is validates, and the partition function value is also given. So now for this case, theta would be simply T by QR. T is 3600 by 19.06, it gives you 188.88 Kelvin. The correct answer would be this option 188.88. Okay. So this is it. Okay. So I hope all of you understood how to solve this problem. So here, this is the actual formula. I think this type of problem we also discussed in the earlier tutorial also. So for rotational partition function for a molecular system, data molecular system. So this is the expression, but in this problem, as you can see, the temperature is very high, 3600. So we have to do some high energy approximation, high temperature approximation, which is given by this. And from here, everything is basically given, the temperature and also the partition function at the temperature, rotational partition function at the temperature is also given. From there, you can calculate this characteristic rotational temperature. So this is it. So I hope all of you understood like how to solve this kind of problem. Like if partition function is given, so many kind of type of properties you can calculate. Okay, you can like first you need to derive from the thermodynamic definition to find out what is the relation. I mean relation of that particular thermodynamic function to the partition function, and from there, if you can calculate the partition function of any system, you can basically calculate from there to the any kind of thermodynamic property. Okay, so that's why partition function is a very important property of any kind of thermodynamic system, especially in this kind of equilibrium thermodynamic system. This is it. Okay, so let me just end the meeting here. Let me first stop the recording.